Well, as an enthusiastic hobby musician myself for several decades, I naturally got into contact with the area of live sound enforcement whenever musicians want to perform in locations that are just larger than a little club stage. It soon became clear to me that there's much more to good live sound than just stacking up more and bigger loudspeaker towers. Producing good live sound is an art that wants to be well understood. The name Meyer and Meyer Sound constantly crossed my way together with a few other prominent brands. And this is where the story of tonight's Heyser lecturer starts. John Meyer's career as an audio innovator was launched in the late 60s, starting out as a designer of custom amplification systems for guitarist Steve Miller, then continuing as creator and the legendary Glyph very large horn loudspeakers and as in-house loudspeaker designer at San Francisco's McCune Sound Service. In the late 70s, his audio research at the Institute for Advanced Musical Studies in Switzerland led to his first patent for low distortion horn. In '79, he co-founded with his wife Helen Meyer Sound Laboratories, a company synonymous with innovations in loudspeaker design and acoustical measurement. Meyer led development of the SIM system for audio measurement, which was awarded the prestigious R&D 100 award in '92. Meyer Sound also pioneered development of self-powered sound reinforcement to loudspeakers with introduction of the MSL4 in '94, launching a trend that since revolutionized the industry. Throughout his career, he has focused on development of linear loudspeaker systems with his R&D team, most recently achieving phase linearity from 20 kilohertz down to 27 hertz with the Blue Horn System Studio Monitor. John Meyer is a fellow of the AES and recipient of the AES Silver Medal. So, ladies and gentlemen, please help me welcome John Meyer with his talk, Taking the Room Out of the Loudspeaker, New Tools for Transparent Reproduction.
Thank you. It's a pleasure to be here. I met Heyser a few times, and after he presented his paper, it was a monumental paper in the sense that it really opened up the idea that maybe we could separate the speakers from the room. That became kind of a quest for me to go forward on that. But I thought I'd start out with some humor first. When I was a kid, I grew up in a radio, I was a radio kid, FM radio, and FM radio in the 50s was the highlight of classical music. It was programs, it was like, it was where music really mattered. FM is an amazing thing because it's full power all the time, and so you don't have to compress. But I read comic books, much to my parents' horror. And theater people don't read comic books. But I bought this, 25 cents. You know, that's not much money. I could have bought 5 ice cream cones as a kid for that money. And I bought this thing, and of course, it was a little reed that you stuck under your tongue, and a book to tell you how to not move your lips. I was disappointed. Then the next one came up. This one got my attention. But I didn't have $1. $1 was a lot of money. But I was in private school. One of the other kids had money. He bought it. And there was 2 little feathers inside the thing. And we were really mad. I mean, it's like, you think there's fake news now. Well, they just figured out a new market for it. But going on, this is a folio from KPFA to give you an idea of what was happening. This is when I was 10. I was doing bit parts for like Sid Sawyer and other dramas. I was a good reader, not a reader, but I could tell from memory. And you can see up there it says binaural. Now, binaural in those days this was pre-stereo, 54. Stereo was going to, and KPFA had 2 transmitters because there was part of Berkeley that you had to have 2 transmitters to make sure we could cover all of the areas. The A transmitter on the hill could cover all of California, but there was parts of Berkeley missing, so they had a B. But there was an overlap area. So binaural recording was like spatial. In other words, you'd have an A channel and a B channel. You'd set up 2 speakers and create a spatial recording with a single instrument. They did this about once a week, along with other concerts and things like that. And over in the corner, you can see I've got a little circle. That's my program. I think the next one will show you. Well, that's the Altec. Altec microphone came out with a condenser microphone that was very flattened. I have 2 of these, and they're very, very good. They were a pencil microphone, and that's what we use for our classical recordings, jazz recordings. We had 2 of them. And I just measured them the other day. You gotta let them warm up for a week because the tubes pop because they have gas in them. But if you let them run long enough, they actually are really good. Very flat. They're a glass diaphragm, gold sputtered thing. Cost as much as a car. Getting those at KPFA was a huge hassle. And this is my more of my program here. Let's see. Here's a snippet of it. This should be playing. Oh, this is test tones. That didn't work. I don't know what happened. Anyway, there was a short. Didn't play. Anyway, you can see I have some CDs from that period if anyone wants to actually hear these stories. But the test tones, you can see at 4 o'clock, were done to hi-fi people that wanted to test out their stereo systems. Just to give you an idea how geeky this time was. My first programs was Snaps and Snails, where I told fairy tales, but let's go on. That's the control room. When I was 12, I got my 3rd class license so I could run the tape recorders, and you can see studio. To the right over there is Studio A, the one for, no, Studio, that's B, I think. Yeah, no, that's A and that's B. And he's actually tuning, that's not me, it would have been me, but I couldn't find a picture of me. He's tuning the receiver because it was required by the FCC that you actually monitor your radio station. So for the picture, he's doing that. Then I started to get interested in getting my 1st and 2nd class license. In the radio stations this time, the engineers, 1st class and 2nd class engineers, ran all the stuff for radio stations. Managers paid the fines, but we were responsible for the operation. We got our license suspended. We had our certificates on the wall. This is 800 Q&A questions. It took me 2 years to memorize this to get my license so I could run, go up to the transmitter, repair a transmitter, service the transmitter. And I took the test. I aced the 3rd class. I mean, the 2nd class was all Q&A, so I got it 100%. It's a Q&A book. 1st class was harder. It was written. And my algebra was only basic algebra, and they gave me one of those 3-phase algebra problems. And I had figured they were going to do this because I'd memorized the 1st class perfectly. And they said, actually, I technically passed, but they couldn't give it to me without taking more algebra. And I was really mad. But, so I renewed my license. They gave me my 2nd class. I kept renewing it. I planned to go back and get my 1st class. The only difference between 1st and 2nd class is that you can be chief engineer with the 1st class for radio or television. And I wanted that, but I was 14, that's what I wanted. And they said I was the youngest that ever got the license. I understand Betsy Cohen, which I met later, got her 1st class license when she was in a radio station, and they dragged her up to the transmitter, but you're not allowed to work on the transmitter unless you have someone 1st class licensed person in there. So it was an interesting time. And this was full of heterodyning. I mean, this was a hard test. I mean, but I had a good memory. But I took a summer class because Oakland High I was going to go into. I was going from private school, and I wanted to go into a real high school that had 4,000 kids. So I went to Oakland High. This is sound crew in Oakland High. This is not audiovisual. This is just the sound crew for the 3. We had an auditorium, full fly, And what we were going to do is we do plays, we did Boy Scouts, we had a Jensen cluster system, and one of the guys in the center is building a tube mixer. These are all really geeky guys. And actually, I think the next one shows me there. I got in with my second-class license, but I came from radio, so I was saying that, you know, we had a carbon arc projector. I said, if we could get that carbon arc projector working, I'll go pitch the vice principal that we could then set that up, play movies during lunch. They were going to close the campus because the kids were littering all over the place. This is a rough Oakland high school in an urban area. And they're trying to close the campus. And I said, we'll charge lunch. We'll charge them 35, 50 cents, depending on our expenses. And I said, if you guys could fix this projector and get it all working, I'll go pitch the principal. Now, one of the things, vice principal, I said, one of the things you learn in radio is how to pitch, which means you anticipate every question that you might be asked you. I figured I had 10 minutes with a busy vice principal. I'm going to go in and hit him on, he says, well, how are you going to do this? And I said, well, we'll charge 35 to 50 cents depending on our cost of the film. And he says, what about cleaning up? Who's going to clean up the mess? I said, well, we got the janitor. We've already told him we'll pay him this much money to clean the place. He's okay. And this went on for a few more minutes. He says, who's going to approve all this stuff? Oh, Edwards is our shop teacher, electronics, everything will pass through him. He goes, okay, don't make me look bad. Get out. So we're on. So we're starting to do lunches and making money. And making money means you can buy things. And so here a Musicaster comes up. Now I came from radio. I didn't know much about speakers, but this looked really interesting. We had this big Jensen proscenium thing in the middle of the air. Made all our stuff come out of the sky. I said, if we could bring some speakers down the side wall, we could lower the image. And this is perfect. Now Mr. Edwards said, I think you might be disappointed, but that didn't stop me. It's our money. We earn this money. I want to go push forward with this. Now, I'm really in a favored position right now. I'm teaching electronics third period or seventh period to seniors that need to get out of high school. So I'm teaching basic electronics in his class. So it's an in crowd, no question. So we go ahead and buy these things. And there's the data sheet. Look, really a flat frequency from plus minus 1 or 2 dB. This was just what we wanted. It was awful. It was shockingly bad. And the worst than that is that you look bad doing it. And toward the end of the 7th grade, I got replaced as shop guy to someone else took over a musician. Just wrote me a few months ago, reminding me that he got my job out of high school, out of a clear blue sky. I go, that's great. What a nice letter to get right before this. But, and so I decided to change high schools, of course, and go to a different high school for 12th grade because I'd lost my status in this world. So there's consequences to these things that are hard to understand when you're in high school. But I moved on, got more calculus, did more schooling, and got a job at a hi-fi store in Berkeley, 1966, to repair equipment. And Steve Miller came in with his band and wanted to do power for his band. And so we chose the Scala, set on the data sheet, went down to 45 cycles. We put wings on it to make it go down to 42 to pick up the bass note. And Don Hemholtz, who's still with me, had his Harman Kardon tube amplifier. We paralleled it, had a transformer so we could get 70 watts out of this thing and drive this thing hard for his bass guitar. And we went down to the Monterey Pop Festival, and it didn't make it to the end of the show. And you go from being John to Meyer. This is my career at State. And you go like, darn, or other kinds of words that are being thrown at you, And I go like, so I bring it back and I cut a hole in the box with plexiglass. I want to see what's going wrong. And this driver is inside's flapping around. And Jim Isom, who's there, engineer, double E at Cal, says, let me look at that. What are you doing? I go, I'm trying to figure out why this thing isn't working at 40 cycles. And he goes, and he comes back the next day. It's not a horn. I said, yes, it's a horn. He says, it only goes to 70 cycles. It's just a piece of, it's just stuffed inside some wood box. I go, oh, goodness. So then I decided I was going to build some horns. So I decided to build some horns from Olson right out of the textbook. And I had the calculus to do this. We changed it to an exponential expansion rate, so we could do it on a Curta calculator, so we could do it like a percentage increase thing. And we built these perfectly exponential horns. This is 8 feet tall, 8 feet long, 30-inch compression driver, compressed. So it should have been 25% efficient. It was about 23. I was disappointed. I figured if it went below, the articles were written by Glyph that horns work below their cutoff frequency would have gone to 30. If it didn't, it would go to 40, which would still make the bass note that I was after. It went exactly to 40. They used to shake around the floor because they were so efficient that I decided one day to come in with a stud gun and nail them to the ground, and it pulled out chunks of concrete. So that it was one of those better. But this was done in quadraphonic, bi-amped, because I was into electronics, and this attracted a lot of attention, and we got, because of the theme and the pictures, I went out and bought a Rolleiflex so I could just take this picture. It got me a job at McCune's, who wanted to build a system for touring for Burt Bacharach and Elvis Presley, and they got the Creedence tour. And I wanted to be tri-amped, but I wanted to get rid of all the electronics. I didn't want anybody to have any controls. I didn't even want an on-off switch. I just wanted to plug it in the wall when you unplug it when you plug it off. All the crown amplifiers and everything are buried behind the panel. It's a 3-way system, all horn loaded, and it had the girth so we could get it on an airplane so we could just ship it, and I didn't want anybody to touch it. And we moved all the EQ to the console. We made strips of EQ with parametrics and things like that so the mixers could have anything they want. They just couldn't change anything here. So I wanted to start to separate the system from the room, and on that quest, and I really didn't want anybody fooling with it. And we used derived networks, which I think were published in the AES, to kind of try to get better phase response. But we had a hard time measuring phase at this time. It was a nightmare. Then Bear from Osley comes by and wants to build a more dispersive, powerful center cluster. And I said, well, let's build it as a barrel. Let's make it 3-way. And I'm already using these EV tweeters, so I bought every single one EV had, which you can see at the row at the top, to their whole year's supply of EV T350s. They liked that order. And we started, and this was the, do you know which one this is called? I can't remember if this is the piano cluster or the vocal cluster. I don't remember the names. Bear built it out of honeycomb. I didn't care what he built it out of. I just wanted 3 ways. Okay, so I wanted to show them that you could get more dispersion. I was showing them Olson engineering and trying to get them into, I wanted to measure the phase response to see if the phase response got better, but he couldn't do it at this time. We came back, we just didn't have the equipment to do that. So, but then Bear also got this idea of using differential microphones, and they weren't working very well. You have one in phase, one out of phase, you sing into one. And I said, well, I think you should use instrumentation microphones. I can get some from B&K. We'll get 2 matched ones. They'll match them for us. So we got 2 matched instrumentation microphones from B&K, and you see singing into one, it actually, because the whole PA's behind you, so we're trying to blast through a wall of sound, and hit the room, so feedback is serious. Well, what happened one day, Bear came over and says, you won't believe this, one of the preamps died, and it's still not feeding back. And you go, what? And you make a middle note, like, that's something interesting, we should come back and look at this. Why would they not be feeding back when we had so much trouble before? Was it flat response matters? It's like, because this is all brand new. I mean, everyone is trying to, it's a complex problem. But at the same time, delay lines came out. So I said, I think we could start, the band did not like playing stadiums with their whole wall of sound behind them. That wasn't going to happen. They were getting killed. So the idea was, I said, we could move some of the sound out using delay lines, keep their source. Bear wanted every person to have a source, like you'd have the drummer would be the source, everyone would be a source of sound. I said, we could use delay lines, preserve the source, and push the image out with these new Gotham delay lines, which cost a small fortune and were noisy and all that kind of stuff. But it worked. I mean, they were like 10-bit or whatever they were, but it gave us a start toward and we hung. And this was early 70s because things were falling off of platforms. So we got this idea we better start hanging this stuff. So there were other people starting to hang in the 70s. It was just starting that whole idea. And this made a close relationship. Then Buell and Kerr came out with a sound level meter. Actually, they won an R&D 100 for it. And what's cool about this sound level meter is that it could do peak, true peak, had like 20 incredible string of diodes that could get the true peak, and RMS. So we could figure out the power of something. One of the things that always bothered me about music is drums. When you look at a drum, you can reproduce a drum peak with a little tweeter, but you need the peak pressure. You know, so when we started, we knew we needed to start to understand that world. This pot costs more than a car, this thing. You know, these were really expensive instruments. I don't know how I managed to get this stuff bought at these companies, but I push. And we started measuring. Then we got this opportunity to go to Switzerland, a grant to do classical music outside and build classical speakers institute in Switzerland. This is a pile of gear that Buell and Kerr was making, all heterodyne radio frequency time delay, you know, and they had this is a 3 hertz offset filter in there, so you could offset the filter so you could do time delay spectrometry. So this was in '73. We bought all of that from Buell and Kerr so we could do Heyser's experiment, is I wanted to go have a classic sine wave sweep, you know, anyway, no matter what. So we put this together. That literally could have bought an apartment building for what that cost. And then the other toy we bought was a PDP-11 driven oscilloscope from Tektronix. This could do 50 picoseconds rise time. This was so fast that we had to get a blue permit from the government to bring this into Switzerland because the military was worried we'd be measuring radar with this thing. And the only reason, all I wanted was the 4-channel FFT that came out of the PDP-11 in its raw form, and this is the only form it was in. Hewlett-Packard had one too, but Jim Isom didn't like the Hewlett-Packard, he liked the PDP-11. And he's going to program it, so this is what we bought, because I need someone, I'm not a computer person, you know, so I need someone that loves computers. It took 4 hours to get a PDP-11 even running after you start with the absolute loader, you know, so it's one of those things that 4 hours later, you make one missed switch and it does not work, even to get the first boot to work. I mean, it's like this was, and the FFT is totally raw. I mean, it's just complex data. There's no, you want to do trig, you do trig, you want to do windowing, you do window. We had to do everything. But it gave me an opportunity to measure the T350, my favorite tweeter of all time from that era. And that's what it looked like. Now, when we measured it with sine wave sweep, to get to that resolution, sine wave sweeps, one of the problems with sine wave sweeps is you have to move them really slow to see the cue. This took about almost 8 hours to get to that resolution that we got to within a minute doing it with FFTs. And so we started realizing that FFTs looked really interesting. The other interesting about FFTs is you don't have to work down to 1 hertz. They're amplitude accurately fast. You can be 30 hertz. You can work with coarser windows. So it opened up a whole window of amplitude accuracy because it's not a chirp. It's not moving. You don't have to, we actually had one from Hewlett-Packard we bought, which was a sine wave sweep that would stop and go backwards. It doesn't help much. All it does is go backwards and then go backwards and go backwards and go backwards. And then it goes forward again, and then it finds the next peak and it goes back and hunts and hunts and hunts. It doesn't speed things up much. We bought lots of things because no one seemed to care what we spent our money on. So we bought a reciprocating counter that could give me 10 decimal places in 1 second from Hewlett-Packard so we could tune pianos. Well, we found out pianos don't tune. I mean, they're like, in 3 or 4 seconds, they're still 3 places. I go, how do you tune these things? I said, the piano tuner. He goes, what do you mean? I go, I've been watching this thing, it's like looking for launch codes. Nothing's happening. Every second I get another number. You know, like it's been 10 seconds, it's still not a note. He goes, so it depends how they play. No, an art form. So we go on, and then we start searching for, loudspeakers are a weird device because you have kind of a compressive suspension system holding it together, and you have an expansive electronic system that interferes with an amplifier with some kind of insane complex circuitry that makes it kind of opposite of each other. And no one had been building linear loudspeakers. So this is a very simple test. I think it came out in the AES. You take an oscilloscope, XY, look at current, put it in resonance and see if you can get a Lissajous pattern. And we searched every speaker on the planet for months and months and months. Finally stumbled across this thing in Switzerland from an Italian company, 1 out of 10 that did this. So we sent a team over there to find out how to reverse engineer it. And from that speaker, we started building a studio monitor called the ACD, because it was the first thing that didn't have a loop or a hook or, you know, like, you gotta look at some of these on a Lissajous pattern, so-called hi-fi speakers. They're a mess. Now, we've tried servoing this later, but that turned out to be a problem because when you do high-gain servos, it interacts with everything else in the room. You put a speaker on top of it, it cancels it and stuff. So we went back to linear theory, which means that you have to put a team together to do this, to try and figure out how to build these complex things that need suspensions and stuff. That became kind of a quest. When we got back to the States, we brought the studio monitor with us linear 12 in there. And we were doing a show with, in Berkeley, showing the studio monitor we just made with this linear transducer, and Bear came in and said, oh, the dead got to buy this. And Tom from Zoetrope came in and says he wants us to, we're building the subwoofer for it. He says we could do this with, for Apocalypse Now. And they're going over to North Point for the next 3 months. They're going to do the low frequency. So there we go, 3 months every day before Alien started. Because they played Alien at noon. That's when most people run. 70 millimeter Alien with low frequency is an experience. But gave me nightmares for months. But anyway, we started doing the 70 millimeter theaters for Apocalypse Now. And we're using the Electro-Voice 18-inch because that's what we were, our product. And we had, after a couple of weeks, we built a power controller. We did thousands of watts of peak power. We were trying to, Coppola wanted to shake the room. He wanted to hear it in the bathrooms. He wanted the napalm to rattle the space. And this took 3 months every day working on this project over there to get that sound he was looking for. Stereo bass, mono bass. You know, stereo bass sounded better, but it's more work to set up, and they were having frequencies, and it was just endless amount. They were looking for one effect. So I sent the driver up to the plastic divisions at the University of California to find out why the voice coil wasn't burnt; it was shearing off. And Electro-Voice was running on polyimide. Now, polyimide is a thermoplastic, but it gases. So it would swell, and it was ripping, they showed me it was ripping off, it hit the side and rip itself off. So I called Electro-Voice chief engineer, and they said they also have discovered that. I go, you gotta fix this. I mean, I said, you know, I don't wanna get blacklisted in the movie industry. It'll be 20 years before I'm back in. We've gotta fix this now, like weeks. And they said, they couldn't fix it that quick. So I got the Italian company to do it for me and build it on aluminum former, but you gotta leave a gap and put a paper space. It's a hassle. But we got that, and we replaced all the drivers quickly, you know, keep the 70 millimeter houses going, and introduced it to the Grateful Dead. I was out of rock and roll at this time. I was tired of rock and roll, but you know, they were in there. They were doing stuff with the Grateful Dead and Zoetropes. You're all back in the crowd again. And Phil Lesh wants to hear our subwoofer, which at that time was called a 650. So he popped the woofer out of it. So I put 2 woofers in the box. It became the 650 R2, just for more mass loading. It wasn't any more efficient, but bass guitars have a lot of oomph. And so that was all cool. And then next door neighbor was working up at the Berkeley Lawrence lab. And he said they just got this new analyzer from Hewlett-Packard called the 3582A, not the A, the prototype. And so we rushed over to see it. And it's our analyzer in this box, everything. Same windows, same length, everything that we had in that Tektronix is right here. And it's like super exciting, and it's programmable, and it's a lot cheaper. And but they were windowing the time record. I said, you know, when we windowed the time record in Switzerland, we got distortion. You know, you get problems if you try and take those echoes out. We did a lot of it. You take all the echoes out and you get down to one little point. It looks really good, like one straight line. I said, you know, how much are we going to window? So they took it out. And they started thinking about putting in periodic noise, which is what we all were really interested in, putting a periodic signal in. And we did some shows with the Grateful Dead, putting in periodic noise at low level, like 40, 50 dB down, and time averaging it out over time, working with Hewlett-Packard. But after about 15, 20 minutes, the crowd started to scream. And Dan, he says, you're going to have to stop. I go, what? Why? He says, they always scream. What are you talking about? I mean, that's all they do is scream here. And he goes, no, they're hearing it. They can't hear it. There's no possible way. The signal is so far buried in this thing. It takes me half an hour to get a recovery. He says, stop. So I finally stop. And they stop screaming. I go, it's a coincidence. Can we just start up a little bit later? So I wait half an hour. As soon as we start up, they start screaming. This happened about 3 times in a row. He says, you got to stop. You can't do this. I said, how in the hell do they hear this? I mean, it's like, what are they? I mean, it's like, it's unbelievable. It's just how people can hear when we don't know how they can hear. You know, it's like, it doesn't make any sense. So that started us on the path that we're going to have to do this with music. It's the only way, only chance we have. Is that if we're going to measure rooms, we need to do this with music. And that started us on our next path well, actually, in the meantime, we built this ultra monitor with that same 12-inch driver. This is with Stevie Wonder, and we actually did it for Kantner, and Kantner did not like this studio monitor. He said he liked the acoustical lens potato masher better. So we dragged it back to work. He had one, and we measured it, and it was like a comb filter, like around it's between 50 and 100 milliseconds if you looked at it. It's not even perfectly, but it looks like this comb. So I told Howard, I said, I think we could simulate that with this monitor. Just take a 100 millisecond or 50 millisecond delay line and blend it with the original signal and feed it and see if that works. And Kantner liked it, but no one else did. And so suddenly we said, so everyone accuses me of wanting to take the salt out. Yes, we'll take it out, but we'll give it to you as a package. You can put it back in if you want. I'm not anti-salt. I just want to start with this thing neutral. And Stevie liked it the way that it was. So linear was becoming more interesting, but it created problems because people are used to speakers having a sound. And if you take it out, they're reluctant to put it back in electronically. I don't know why. They think you're cheating somehow. It's like, it's okay if it's a speaker doing it, but it's not okay if you do it purely electronic. I think that's changing, but it's still been a kind of a struggle because it's what we kind of want to do. So we started working on a paper. Betsy Cohen was going to help us. She's around the Grateful Dead. She's double PhD. She's at Stanford. So we made a trade with Stanford to do a paper, and they would give me technical people, scientists, and I'd give them speakers. And we'd trade back and forth. So we started working on this paper to show how what we're learning using music in the field. And Betsy, this paper was about 1 inch thick. I had lots to say. And anything I couldn't defend, she'd read out. And so it got about 5 pages long toward the end of this thing. You know, she said, can you defend that? And I go, well, what do you mean? Boom, out, it's gone. You know, she's ruthless, unbelievable. But she wanted to do this chart, starting with sine wave sweeps all the way up to the goal, which would be constant Q, which hadn't been done yet, you know, a constant Q transform, you know. So this would be the goal page, which created a lot of controversy for some reason because we kind of put it in a simplistic chart, you know, kind of like of what we saw it at the time, like what the technologies could offer and things like that. It wasn't meant to be good or bad or anything. It was just a chart of kind of the data. They didn't publish this paper. There was a lot of controversy for some reason. But what really got us into trouble was I walked by Bob's bench, and we were building bi-quad filters. And Bob had this on a screen on the Hewlett-Packard. I go, what the hell is that? Where'd you find symmetrical filters? He goes, oh, it's in this electronics world. And we go, Jesus, are you serious? It's a symmetrical peak and dip. I haven't seen one of those. This is complex, Rube Goldberg, lots of pots, dual things. I mean, messy. Now, Mike Toronto was there, an engineer from Lawrence. He says, I could clean this thing up, make it much better. And we knew that in parallel filters, like we knew from 1930 that you could take a filter, split it in high and low, first order filter, and resum it, and it would recombine. That was known. So we're building this in parallel filters into a summer. So that would work. And we had an A channel of 5 filters and B channels of 5 filter. What worried me is what happens if someone put them in series. I woke up at 2 o'clock in the morning, ran down to work, put 2 of these things in series, and it disappeared, and the delay disappeared. So I called Dr. Julius Smith in the middle of the night. I said, you won't believe this. He's the filter expert at Stanford. They're disappearing. Well, I'm seeing the same thing I'm seeing when we're doing parallels. That's impossible. He says, if that's true, he said on the phone, that would imply group lead. You know how controversial we'll get if we talk about this? We're all good with group delay. phase delay, we like those numbers. Group lead, oh my God. And now Channing said, they all had a big meeting, Betsy, except for Betsy and me, we were in the cafeteria, and they decided that they wanted to have 20 years to put their head around this problem. It got worse because in the meantime, I was outside seeing if I could EQ echoes with this thing. So now we're outside having Bethany witness taking out echoes on damp boards and things like that. Maybe their minimum phase, maybe this would work. And they said, we can't release this paper. I said, well, I'll do it myself then. He said, it'll be 20 years before this will be a 20-year controversy. 21 years later, I got my silver medal for this work. You should listen, young people, you should listen to your advisors. You really should. It just means a lot of grief in the meantime. But the Grateful Dead bought the B&K version of this, which had a bigger window. We wanted to use it for our analyzer, so we started a team. We hired an engineer from Buell & Care. We're using LabVIEW. It worked well, except when LabVIEW crashed, it took 30 minutes to reboot, which is too long for us in a live show. And so they thought I could get it down to 15 minutes with a lot of effort. Bob McCarthy had another team. I generally do parallel teams in the company. And so Bob, this was giving me credit for the work. And Bob built the 3582 into this thing, programmed it so that we could actually get the order out that we promised because we couldn't get the B&K done. Even though the Dead bought the B&K, it was a nice instrument. It just was hard to, this was easier to program. Hewlett-Packard was just, it wasn't easy. It was like a huge amount of work, but at least we could get out in the field with the thing and start to do some work. Paul Verratti, Grateful Dead, and start to look at how we're going to do this. And right away, we won the Tech Award, which was amazing. It was one of their first ones. So it was exciting times. And during this period, in 1969, the Princeton Applied Research got the R&D 100 for FFTs. HP 35 got one in the 70s. The electret microphone was invented in the 70s, flared fluid, 4-channel digital. So there was a ton of stuff coming out in our industry during this period of time, things that were just amazing. Time was just, it was an exciting time. But now, what happened here? All right, this was, I'll get to my notes. All right, this is the, when we go back to Glyph, Altec wrote a paper on coplanar, like if you put the driver's coplanar with a second order network, you have to flip the high driver in order to get a flat phase frequency response. And then you wonder what happens to the phase response, because we couldn't see it at that time. So they said, well, you could flip it back and forth and listen to it musically and see which one you like better. That does not make me happy. I'm not that kind of person. I like things that are absolute. So this was the first chance we started to see a flipped phase driver. Now we've got a new problem. What does it mean? A rack in the phase response. And what do we do with it? So suddenly we've got this rack in the phase response, which is already it's hard to understand what phase is. It's the notes are pretty easy. They're just notes, but phase, what is that? It's the order of something, order of these things, harder to understand. And a rack in the middle of it doesn't make anything easy, but we can smooth it. And you have to smooth, if you're going to do, one nice thing about group delay or phase delay, which comes from radio, but if they're flat magnitude, then they're the same. So you can talk about this just as delays. If you have a flat magnitude response, it's just delay. But you have to smooth it because the noise will kill you. So this is third octave smooth, which means it's got some distortion. Matter how you smooth it, it's going to have distortion, but it just gives you a feel of something that isn't a phase rack. It means that certain frequencies are being delayed compared to other frequencies. So it gave us at least a glimpse of a tool. Then EV came out with a corrected frequency response for the, in 85 for the Musicaster that I bought. And it sounds the way it looks here. So I was satisfied at least we were becoming honest in the 80s, as magazines and things came out. I think hopefully that'll come back where, that kind of idea of being, we just need to know. I mean, it really is hard on people when you don't know what's going on. Then the next project, when we're doing SIM, is we needed a speaker that would not move around. We were trying to figure out how to measure a voice or measure something in a room. So when you have someone stand there and talk, they turn around, they look around, and it messes up your work. So I wanted a 50-pound speaker, totally phase corrected, amplitude corrected, that at 1/2 meter would have a flat frequency response and a flat phase response, no racks. This was a lot of work to build. It's 50th order, lots of filters in it. It's about the limit you can do with analog before they become unstable. And this was its magnitude and phase response. This is out of the studio. I just did it the other day, just grabbed one. You can see the yellow line is the high resolution and the blue line is filtered. So it's very flat at 18 inches. So you can test your field microphones quickly, make sure you haven't dropped one. Unfortunately, Roger Nichols came into the studio to listen to the thing and decided that he had to have them as a studio monitor. I go, it's not a studio monitor, it's a test box. I don't even know who let you in here. And he goes, well, I'm not leaving, he says, until I get them. 3 days later, he had them, did Ricky Lee Jones, he was Wild Cowboys. We're on our path to building studio monitors. We didn't even know how we were going to build it. We had no clue. We're going to make 10 of these is what is our lifetime goal for testing. And that's how this thing surfaced on the planet. People still use this thing. It has no racks in the frequency response. Still, we have the phase delay. And that's just, we were going to live with that. Then we started getting more interest. Los Alamos published an article in the newspaper about measuring salmonella with music and eggs. So Helen called them and find out what that's about. And they said, we have a machine that we think we could do it really quick with music. So we drag our prototype machine down. They're doing sine wave sweeps, which take 8 hours to find the high Q things they're looking for. We did it like in less than a minute. They said, we should go for an R&D 100. I go, what's an R&D 100? They go, they have a wall of them, of course, and they're explaining that, well, you'll need an endorsement, we'll give that to you. You need a paper written, and you'll have to publish all the algorithms. Now, I was going to patent this. This is a lifetime's work that we've done. And Jim has done most of the work. I have to talk him into doing this, that we're going to give this away. Why are we going to give it away? I think it's more important that we give it away than we keep it as a Meyer thing. They'll just basically say, oh, it's a Meyer thing. And this way we can push it forward and create interest. That's my thinking at the time. So we wrote, I think it was Cabot that I called up and I said, I need a paper. And he said, someone just dropped out. You can have theirs. So we had the paper. We had 2 weeks to do all of this, to get this submitted. 10,000 entries that they told us we were up against. And we built a SIM2 machine, and this was a chip that Bell Laboratories was building, and they were only going to do magnitude only. And we pushed and pushed and pushed to get complex data out of this chip so we could get phase information, and they did it for us. And this chip wound up, did some work with Martin Marietta, and they wound up using this chip because this chip was super powerful. And it was the whole next generation of technology. So that was really, I was getting some hits around that I wasn't just alone in all of this. Now, this is a test of coherence in this machine that we're building, which has, you can see there's A noise and B noise, 2 different pink noise sources, and it should be 50%. And if coherence is working correctly, now this is for linear systems, because we're building what we call a sparse analyzer, meaning that we're not, transfer function can be taken over time, or we realize that. We don't have to do it in real time, as long as the systems are linear. You just have to piece it together. So we're taking chunks of data to build up our transfer function. It's like, someone explained one time to me, it's like figuring out if a lemon is sour. You don't have to do it instantly. You just have to figure out if it's sour. That's what you're after. So the transfer function can be built. And so this SIM2 machine can give us a valid transfer function, as long as you're not clipping or you have other forms of distortion and things like that. So that became our, and we got the R&D 100 for this, which was really, really exciting for a small team of ours compared to these national labs, which have half the room filled with people. Then Roger Swanky joined our company, Dr. Roger Swanky, and then we wanted to decide to build a real-time Fourier analyzer that would have 2,000 FFTs a second. All data would be accounted for. And that was our SIM3 machine. It was going to be our research machine to do STI and speech intelligibility, look for nonlinear things, look for a frequency response. Like if you're in the field and you're watching wind goes, you see the wind that goes down, then it goes down more and it comes up. It never goes high. It always goes 0, low, low, lower, 0, lower, lower, lower. So if you average it, it's always less. So if we could capture it in less than a second, you could wait till it stops and bang it. So it had some practical field use. And it's not necessary to measure linear systems, but it is if you want to start measuring nonlinear systems. Now, my son was in math, started working on these boundary element programs and finite element programs converted into building horns for us. So we could build more precision horns and field things that would be very, very, very precise, very even fall-offs. And these methods allow you to do Monte Carlos and iterate and make really amazingly. So this is a project that we did for Skywalkers. They wanted a midfield monitor. So it was a chance to push the near-field monitor a little further away and get into 5.1 and things like that, but with very controlled vertical and horizontal control so we don't hit the console so much. This is very narrow vertical, a little wider horizontally, and they do these as 5.1s. And this you couldn't do without the mathematical modeling we have today, because everything comes into play, the cabinet, shape, everything. These modeling tools, we rent these tools at $40,000, $50,000 a year from these places that these are all licensed programs you buy, but they're invaluable tools. If we had a supercomputer, of course, we could speed it up, but they're like 20 grand a night to run those things. So we do an iterative, we do a process, and then we build a stereolithography, and then we do another iterations or two, and then it's not fast, but it's in a couple of years you get results. That's its frequency response. You can still see for the AMI, we generally do a hybrid outdoors. We'll do the low frequency and indoors. In the anechoic chamber, we'll do the high part to get away from, we'll do a big open space. We still have the phase delay problem with the low frequency. Then this is this delay characteristic between the HD1 and the AMI. If you look carefully, you can see the green. We ran out of all passes. There's only so many all passes you can put in the high frequency before they've gone unstable. And so you can see the AMI is a little bit different than but they're both very flat. This is the AMI 60 feet in the air and then bring it to a ground plane, showing the ground ripple, how they interact. So you can, when you do a ground plane, you got a couple of dB of error compared to a pure anechoic chamber, but it's a fast test, at least you're within the ballpark. So when we started on the Blue Horn project, this was gonna be a team to try to get rid of the low frequency phase. So Perrin headed up a team to my son to start a digital team of very high resolution phase correction, 125 dB dynamic range for the ringing of the filter. So we'd have really, really low ringing. That was the electronic part. And then we started on a linear path to get rid of resonances, we pushed the high frequencies out past 30,000 cycles, so we wouldn't have any resonances. We didn't want any resonances because resonances are, they have a seed, so once you hit them again, you got a new problem. So if you get rid of all the resonances, we wanted to make this thing as neutral as possible. And then the next, so this is what we publish for the Blue Horn. This is at 6 meter outdoor response. And this is in the patent. Took us 5 years to get this patent. They were really difficult. It only shows going to 16 kilohertz, but the later version got bumped to 96 kilohertz. So it goes up to 22 kilohertz now. It's flat frequency and phase. You can see that so what's really cool about this is you can bring this in a room, measure it close, and you see that flat phase response. You can move in the room, you can start to see the room. First time we could separate the room from the speaker. So we can start to see what does the console do, and is it minimum phase, and can we subtract it? And so this is a whole new opportunity of research. It wasn't meant to be a studio monitor. This has been a 5-year project just to try and get this to be something that we could start to rationalize. The whole quest, which Heyser suggested, can we measure the speaker in the room independently of the room? That's what this was all about. It's what led the thought, And so what we have here is now that we're going into the nonlinear world, we developed, one of the things about pink noise that's really interesting is that it's like watching a pond with waves that are the same all the time. And you can chop up pink noise to an octave and it's still 12 dB. It's very robust. But music's not like that. Music's like watching the ocean, and the waves stack. Pretty soon you'll see a great big wave, and then later you'll see maybe only one all day long. So we took 2 years measuring thousands of pieces of music to come up with a statistical way of guaranteeing roughly every 10 seconds we'd get a peak by stacking, so that we would create something music-like that would be repeatable. So we'd get these 18 dB peaks guaranteed somewhere between 9 and 11 seconds, roughly, because it's still, and so this is what we call our end noise signal. And what we're going to do is I'm going to show there's 2 videos around this, but I'm going to show you a little 10-minute video. This is a pre-release, which we're going to put on the internet about measuring nonlinear systems with these new tools we're developing. So hopefully that works.
M-noise has properties that are more like music than traditional pink noise. The introductory M-noise video described the properties of this new test signal and the reasons for its development. The real-world SPL video demonstrated a procedure to measure maximum SPL. It was also shown that pink noise is not able to represent the maximum SPL capabilities of a loudspeaker for signals other than pink noise. Please watch these 2 videos if you haven't seen them already. This video illustrates how to use M-noise with the procedure from the real-world SPL video to quantify the onset of nonlinearity in a loudspeaker. M-noise can be used to predict the maximum SPL of a loudspeaker for music reproduction, but only when using measurement equipment that meets specific requirements and is connected in a certain way. The playback device and microphone must preserve the properties of the M-noise signal. The analyzer must detect any changes to the M-noise signal. The maximum SPL procedure shows the onset of nonlinear reproduction as the upper limit of the loudspeaker's capability. The input level is increased until the onset of nonlinearity. This was shown by a reduction of the transfer function gain. Changes to coherence were not discussed in the previous video. Such changes also indicate that a loudspeaker is behaving nonlinearly. The coherence function is a complex computation standard in the modern FFT analyzer that indicates the quality of the transfer function. We can think of it simplistically as the ratio between signal and noise measured in percent. There are 3 conditions relevant to our application that commonly degrade coherence: reverberation, distortion, and uncorrelated sounds, sounds that are not part of the original signal sent to the loudspeaker. The reverberation time in this room is much longer in lower frequencies than in mid and high frequencies. A loudspeaker measured in the far field shows ripple caused by reflections, especially in the lower frequencies. The coherence is less than 100% across the usable bandwidth, but is most notably degraded in lower frequencies. When the input level is increased by 18 dB, there are no changes to the frequency response or coherence. Reverberation and reflections are both linear. They do not vary with level. This is the furthest microphone in this room, which has the most ripple and lowest coherence. As we move closer, there is substantially more direct sound while the reflections change very little, which causes the frequency response to move up and have less ripple. It also causes the coherence to improve. There is more signal in proportion to the noise, more direct sound, less reflected sound, improved coherence, and higher SPL. In the near field, the direct sound completely dominates the reflections and the coherence approaches 100%. For the remainder of this video, all measurements will be near field unless stated otherwise. Coherence is also degraded by distortion. To isolate how distortion affects coherence, a near-field microphone and a particular type of analyzer are required. Back in the 70s, we voiced sound systems with 1/3 octave graphic equalizers using pink noise and real-time analyzers with 1/3 octave resolution. Such measurements are single-ended and can only quantify the energy over frequency, not how accurately the original signal is reproduced. To illustrate how a pink noise measurement is affected by distortion, an external harmonic distortion generator is added and set to 50%. The meter does not indicate a significant change to the signal. It's also not easy to hear. However, when music is played, the distortion is clearly audible.
On this journey, some doors we'd never take.
If you can't hear this difference, you need a different career. The transfer function analyzer is capable of detecting distortion because it compares the reference signal to the loudspeaker's acoustic output. This is an M-noise measurement without distortion. When the harmonic distortion generator is added, the coherence is degraded, which indicates the presence of harmonic distortion and a reduction of sound quality. M-noise measurements require an analyzer capable of detecting this type of nonlinearity. Uncorrelated audio of any type is effectively noise. The coherence will also be degraded by any sound that is not part of the loudspeaker's original signal. If an uncorrelated source adds continuous broadband noise to the signal, this can be easily detected by any transfer function analyzer. But if the uncorrelated noise is not continuous and/or full spectrum, then it is possible for its audible effects to be missed by an analyzer. In order for an analyzer to show the reduction in coherence from every interfering noise, it must analyze every time sample at every frequency. Some dual-channel analyzers, including this SIM2, do not analyze every time sample at every frequency and will sometimes miss events that should show reduced coherence. Only when the interfering noise happens to occur at a time and frequency that's being analyzed does it affect the coherence. For the purposes of this video, the phrase real-time analysis will refer to analyzing every time sample at every frequency. Transient noises can be used as a test to see if an analyzer is truly real-time. Even though SIM2 does not analyze in real time, it still accurately shows the linear frequency response of the system. However, the M-noise dynamic capability test described here requires real-time analysis that can accurately measure transient signals and transient interfering noises or distortions. M-noise contains transient peaks at random intervals. Random peaks of at least 17.5 dB above the RMS level occur at least once every 10 seconds. If these peaks are not properly reproduced, it is considered transient distortion. When M-noise is used to measure the linearity of a loudspeaker, real-time analysis must be used. The reference signal location is important. Let's change the source to a keyboard played quietly in a low-noise environment and then measure the transfer function. Notice the level is very low, both for the reference and microphone signals. If the keyboard is played loudly, the transfer function doesn't move up or down. Because both the loudspeaker's input signal and the acoustic output increased by the same amount. Let's change the source to a test signal and increase the level. The transfer function remains the same because the gain change is before the measurement reference point. The drive level should be adjusted here during the maximum SPL procedure. From now on, this will be referred to as the playback level. A level change after the measurement reference point causes the transfer function to move up or down because the reference level does not change, but the microphone level does. Don't adjust the level here during the maximum SPL procedure. Note that level adjustments after the measurement reference point are a normal part of system optimization. System optimization must be completed before undertaking the maximum SPL procedure. The playback device needs to be capable of accurately reproducing the M-noise 96 kHz file. This Galaxy processor provides enough drive level to reach the maximum output of Meyer Sound loudspeakers. A sound pressure level meter is used to measure the peak and RMS levels. The microphone must be calibrated to ensure accurate measurements. M noise has a crest factor that rises with frequency. To accurately measure the peak SPL, the microphones must have a flat response up to the very highest frequencies. Many environmental sound level meters and their microphones do not meet this requirement. The microphones must also be rated for more SPL than the loudspeaker can produce. These or similar quality tools will be needed to accurately measure a loudspeaker using M noise. These are the steps to determine the playback level for the onset of nonlinearity. The microphone should be placed close enough to the loudspeaker so that the coherence is at or nearly 100% within the usable bandwidth of the loudspeaker. Use the playback device to play M noise. Choose an initial playback level that is expected to be within the loudspeaker's linear operating range. Store this trace. Increase the playback level by 3 dB. If the signal is still being reproduced linearly, the frequency response and coherence of the live trace will match the stored trace. Store this trace and offset it by the smallest reliably measurable difference. In our experience, 2 dB is the smallest reliable difference. Increase the playback level. Stop increasing the playback level when the transfer function matches the offset trace across at least 2 octaves. This is the playback level at the onset of nonlinearity. At this playback level, wait at least 5 minutes and look for any changes to the frequency response or coherence. Using the SPL meter, verify that the peak hold level is at least 17.5 dB greater than the RMS unweighted level. This independently verifies that the M noise signal is being reproduced properly. These steps determine the playback level for the onset of nonlinearity. These are the steps to measure the maximum SPL. Choose an on-axis position to measure the maximum SPL. Reset the SPL meter's peak hold value. Restart the M noise playback at the previously established level. Store the peak hold level and the RMS level. Continue the test for at least 5 minutes and store the SPL meter levels again. These should be the same as the initial measurements. Sometimes loudspeakers are used at or near their maximum output for several hours. Meyer Sound continues this test for 2 hours. This procedure determines the SPL of a loudspeaker at the onset of nonlinearity using M noise, which can be used to predict the headroom for music reproduction. This is valid only when using measurement equipment that meets the requirements listed and is connected in the manner described in this video. Reproducing music is the most common application that tests the limits of a sound system. Using a test signal like M noise, which reveals a system's SPL capabilities for music reproduction, is a significant advancement that benefits the industry at large. Meyer Sound continues to innovate, making improvements as our understanding evolves.
So we're on time. So any questions? That was quick. Thank you.
Hello? Okay, you are showing all of these responses as a single line graph, which is presumably on axis the way you show the microphone in the pictures of the test?
Just for the video, just to make it easy to follow.
So you also construct polar diagrams?
Oh, of course, yes.
using the same techniques.
Yeah, this was just, we're going to do a series of these films. This was the first one to kind of give people a feel. We're getting nonlinear systems that are, when we built speakers, we have peak limiters and we have RMS, we have all this data to make sure we're not clipping anything. That's kind of going and disappearing. So we wanted to kind of introduce the idea that we need to start doing this with technology. You can make sure that the stuff that you think you're looking at, things like pink noise and things like that, and third octave is not going to show you what we hoped it would show you. So this is an introduction to kind of, we'll do more of these things in terms of looking at more complex systems. So I didn't want to get this too complicated right away. Just kind of give people a feel that you could get away from the room pretty easily at a meter. You didn't have to be like an inch away and things like that. Some of this was unknown for us too, you know, this whole video.
Well, the peak in the treble region is something that I've known about experientially, but thank you so much for quantizing it and putting it into a repeatable system so that we can all design to it.
Yes, well, you're welcome. It's been a pleasure.
Hello, John, and thank
Hi.
you very much. Since we're at the Audio Engineering Society convention, and I know Helen probably remembers this, I have a very short comment for everybody. Around the time you mentioned that paper was not published, you gave a verbal presentation at the AES Convention.
That's
at a
true.
paper
That's
session.
correct, yes.
I was in the room. Is Mark Ureta in here? Mark is my witness, and I still have the cassette tape that I bought from Mobile Tape.
I'd love to hear that.
I'll digitize and get you a copy. So here's what happened. John got up and started by announcing the title of his paper. And another one of our colleagues, an AES member, stood up and interrupted you. And he said, young man, this is a learned society of knowledgeable professionals. We use the scientific method and we accurately describe our conclusions with proper vocabulary. You cannot equalize the room. You can only equalize the sound system in it. So I'll get you a copy of that tape.
Okay, yes. I've always felt like slightly an outsider, but I love this. I mean, I could have had careers in other industries, but music is what I love, and this is my home.
Well, we're all here to tell you that you're not an outsider, and you're giving the Heyser lecture at the AES.
Well, thank you very much.
Thank you, John. That was more than informative. In the near the end of the video, and I have to say, a compliment to your colleague, the narrator, very professional.
Yeah, Bob's really good. I mean,
I see who it is. It's like, oh, his book is quite professional too. You said, Bob said, the signal for the industry.
yes.
So, is this for the industry to share?
Absolutely. We're putting together, we have you can call our factory, we're hiring someone to help. I want to make sure, I want to do it like Linux or free, but I want people to change it. We put a lot of this, movie people like it. I want to keep it solid, but I want it out there. I want it to become a tool, and we're not gonna sell it. I don't know what it's called. I'm not good at software. It's like Linux where it will be kind of like, if someone has a good idea, we'll collectively together and talk about it. I don't want everyone to just go off. And this has been it fits right now in the SMPTE window, which is 21.5 dB, which is really, really nice, you know, or they have 2 windows, but I'm talking about true peak. And so it fits there, so we can use it for movies and things like that, for looking at cinema systems. And so I kind of want to keep it that way. The analyzer, SIM4, we're going to call it SIM4 Lite. We have it all in C code. If someone, you know, we've got people interested in that. We've got that tool we can make available. You know, we're not interested. This is how we don't make our money on this. This is our industry. This is what we need to work well. So my intention is not to get into the licensing business, just to make sure that we do it correctly is all I care about.
Fantastic. Thank you. Are there any other questions? There must be questions or comments.
Yes.
Hi, I'm Wes Dooley. We've had the pleasure of talking a couple of times. Richard Heyser was a mentor and a friend of mine who introduced me to many things. I'm always interested in trying to port things that are developed for one purpose into some other use. And of course, my interest in particular over the years has evolved. We once had a conversation about a conversation you had with Harry Olson about ribbon microphones.
Yes.
And I have wondered, looking at this signal source, how I might use this to characterize another transducer in that circle of confusion that Richard introduced me to, which is, I'm always interested in looking at the dynamic characteristics of ribbon microphones.
Yeah,
Would you like to comment about that?
Yeah. Well, there's some, we actually have some we do in testing. They're like little thermal gradients that we use for looking for in rooms and things like that, which is like a ribbon, miniature ribbon microphone. We can see the boundary. I mean, not the boundary, but the particle velocity and things like. So we do particle and pressure to figure out directionality and stuff. I think this is a whole new world that's opening up for us in terms of what we're understanding about rooms, which is we're getting papers. There's people from other sciences that's going into rooms. And instead of thinking at all, it's just this pressure, the way that we're taught, we're doing experiments now. Like you can tell when you put a speaker far away, when we're doing this experiment at Zellerbach, you can tell they're more powerful than the ones you put close to at the same level. I mean, it's just, we go back and forth. I mean, there's just so much we don't understand about this dimension we're in, that we're just barely starting to understand that dimension, So it's an exciting time because all this wave field synthesis, everything that's going on is pushing in this new kind of envelope how we hear, which I don't think we have a very good idea personally.
Well, one of the things I was looking at there was the coherence function and the fact that you had two microphones up. And I started going, okay, so can I use that setup to know what my signal source is, because acoustic signal sources and knowing what they're actually doing is really difficult in real-time wide dynamics and wide bandwidth. Yeah. So can I put up a third microphone
you
then
can
see where that coherence sits with the other two?
Yeah, our SIM3 is a full 3-channel system. I want to introduce a single channel system right away to kind of get this going. Otherwise it gets complicated and takes a lot of classes. So I'm looking for simplicity to start, but it's easy to expand on these things. I mean, you can do 2,000 FFTs in a millisecond now. I mean, processing power is not our problem. It's how to get people to understand how to use it. If we go too fast, everyone's just going to get overwhelmed. And we're trying to introduce the idea that you need to start thinking about nonlinear systems that are entering into our world. It's not just in speakers, it's everywhere. We're losing vibrato, stuff is disappearing, people don't understand jitter. It's everywhere. When I was growing up you got to remember in the 30s, they found flutter and wow. By scrape flutter on the heads of tape. People heard it in the movie theaters and complained on piano notes and violins. I mean, where's that generation that made the movie industry go find professors and people to build flutter and wow meters? We still need them. We're still we're sampling and crunching data like it doesn't matter. So we've got a huge body of work in terms of in front of us because everyone wants to just make this thing immersive and complicated, and we have to go very carefully into this, or we'll lose the music. I mean, you talk to people that do music, like you listen to them talk, they're talking about it in a way that we're not talking about it. How they lead, how they listen to the future, how do they beats and stuff like that. They're in one dimension and we're in another, and that's what worries me. So I want we at least got our tools to work and make sure we're not overloading things and fooling ourselves with distortion, thinking that people like distortion. It's being introduced to consoles. People are starting to add it back in. I'm all for it. It's fine. But these are like, how are we going to do this? What are we doing exactly? I mean, and all this is we're like in a whole new foundation. I haven't seen anything like this since I was a kid, the kind of this revolution that's going on when thinking. It's all over the place. I mean, it's just like wild. People are promising three-dimensional things sitting next to you. I don't think that's going to happen tomorrow. But like, there are stuff happening though, in things, so, I just want to go very carefully at this point and not lose what we started out to do.
Back in the 70s, I was vice chair of the LA section one time, and I asked my chair what I was supposed to do. And he said, well, if I go away, I need you to do that. And so once before, he was going to be around for a tour, and I got to tell about a distortion workshop that Richard Heyser was doing for the LA section I'd organized, because he'd also told me, organize things that might be fun and interesting, and Richard was a near neighbor, and I said, well, could we do this distortion workshop? And it was great fun. Someone asked what were the requirements, and other than paying your money, and I said, well, pay your money, and it would be handy to read and write in English. And I got laughter. And I'm a tech geek. I had never been in front of 150 people, and they laughed at anything I said, and it was really fun and a revelation. But at the workshop that we did on a Saturday, Richard started with a loudspeaker, and he said, okay, there's standard measurements of distortion. He kind of rattled them off. But let's start with real stuff. And he had a loudspeaker, and then he held a big piece of cardboard and started reflecting sound so that we had interference waves. And he said, you can all hear that. That's distortion. But there aren't any easily done metrics for that.
Is there a question in here? I'm not following.
Okay. The question is, when you work up metrics like this, are you thinking past that? As I said, my interest is transducers at the other end. Were you thinking at the time about that? How far in the circle?
Well, we're showing big things here. We're showing room as linear, which is a huge, huge thing. It's been an argument for a long time. We can show we change gain 20 dB and nothing changes. Rooms are very, very, very linear, which is an exciting thing, which means that, can we deal with it? My idea of dealing with rooms is dealing with the room. I don't think we can create a house curve to deal with a room, personally. I think we have to deal with the room as a room. That's what we're trying to do here, and deal with if you have a speaker and we're playing a violin over there in a reverberant space, and it's a dry violin, it might sound good in the room, but in a dry room, it might not sound very good. So how do we equalize these things that way? You can't have one, you might want to EQ the voice, but you don't want to EQ the violin. So it's going to be, in PA, people look at it like, I've got all these channels, so I can EQ all these things independently. But sooner or later, it goes down to a wire and feeds the speaker. Movies people could do the same thing. You could do the same thing. You can have all these multi-channel, you EQ the voice you want, you EQ this way you want. And sooner or later it gets summed into a solution. I mean, one of the cool things about linear theory is that it keeps track of it. If you put a violin and a voice into a speaker, it reproduces as a violin voice as long as there's no distortion. So we have some incredible tools that were given to us before the 30s. I mean, this all came way before the 1930s, these tools. But I don't think we're using them very well yet. I think we're at the beginning of thinking, because we've got spatial problems we have to think about. Like if you put 5 speakers up, and we do these experiments, you play 5 notes, and you sit in one place, sounds fine. Then you play those 5 notes on one speaker, it sounds fine. But if you walk around, you have 2 different experiences. It's not the same experience, because those notes in those 5 speakers do not completely cancel. They cancel in little places in the room. Where you cancel them electronically, they're gone. So we're playing with these dimensions as though they're absolute, but we're working in 3-dimensional spaces. So we're not near ready to really say, do we have the answers to these things? But I think we can start create tools to make sure that we're not just creating distortion so bad that it's not even, and people are making decisions with those pink noise distortions. They're making effects of what they think it sounds like. And distortions adds energy. You just don't see it on a third octave. So this was a kind of get us back to more how we could use the tools that we've invented to kind of make sure that before you start a long, complicated test, at least things are working the way you think they're working. Like you get the speaker running, and then you move out in the room, you get the SPL, and you see, okay, we've got 114 dB peak. Well, you shouldn't play your music louder than that right now, because that's all we really know from the M noise. So at least you can play all your music and stuff, or watch it and make sure we're not clipping it or doing something. If we want to get good data, and that's what I'm trying to get back to, is the kind of more fundamental looking at this thing. And that's why we did this video, because it forces you to think through it in a concise way. You know, I mean, you got about, TED Talks to me are 14 minutes. I want to get this done in 10, you know, because that's probably the limit of what you can stand on something like this. But like little chunks of time of things. There's a lot of data in there. I bet you some people will watch this more than once. There's a lot of stuff. We've worked a year on this thing to kind of get it to put in the pink noise thing. We built that whole distortion analyzer. And it's a bitch to build a harmonic distortion analyzer that has a total flat frequency response and the same distortion from low to high frequency, not get aliasing problems. We built that twice just for that one shot. You know, it's kind of like what you never would do. You'd do some kind of mixer kludge thing, and it would never be repeatable. We built a little box, put it all inside, so they could take it into the field and I can loan it to people. It goes from 0 to 100%. You can dial it in and you ought to hear what 100% sounds like. You think 50 is bad, you know. And so it's a way. Video is a way of building tools to kind of push us into what it is we're trying to understand. Anyway, I'm rambling. Okay.
Well done. Thank you, John. At this time, I'd like to invite my co-vice chairs.
One last thing. I do have some CDs from Snaps and Snails if anybody wants one. No.
So, my colleagues, Michael Kelly, Vice Chair, Jürgen Herr, Vice Chair. I'm Steve Hutt, and we would like to present John with the certificate, the Heyser Award, and thank you so much for such a fantastic story.
It's truly an honor, and he was truly an inspiration. He really was. So it's a real honor to get this. Thank you very much.
Thank you, John. Thank you very much, ladies and gentlemen. And with this, we move on.